functions, okay? So in order to generalize the functions from the calculus 1 to calculus 3, or from function of one variable to the higher dimension. The way we did it in two different groups. The first group was a vector valued function. Remember, and an object, a moving object, the t was the time, r of t was a vector, the position functions. So that function is a vector valued function. So the domain is a closed interval. The domain is a closed interval, but the range of the function is in R3, on R2. Then what we did all these, tangent line, normal, etc. Then later on in chapter 14, we introduced a new function. That function was a function that the domain of the function was in R2 or R3. Okay. So that was a function of 2 variables or 3 variables. But the range of the function was numbers. So they were real valued functions. So real valued function of 2 or 3 variables. Now what we are going to do now, we are going to combine them all together. So we are going to introduce a function. Okay, we are going to introduce a function whose domain is going to be in R2 or most of the time in R3. So you may be involved with 2 variables or 3 variables, and the range of the function is going to be a vector. So the range of the function is going to be a vector mostly in R3. Okay, so this is the most general function that you can have. This group of functions, we are not going to refer to them as functions. We refer to them as vector fields. So when we talk about the vector fields, your vector fields can be a function whose domain is in 2-dimensional in R2 or in R3, and the range of the function is range is a vector. So if you have a plane vectors, your range is going to be 2-dimensional, the vector with 2 coordinate function. If you are going to be in 3-dimensional, it's going to be 3. Okay, so that's the idea. So what we do is just starting over. We introduce this function, differentiate it. We talk about differentiation of this function, and then we go to the integrations. When we get to the integration, the situation will be quite interesting and different. Okay, so I better talk about those preliminaries first. So today we are going to build the function. Okay, the way we are going to do it today, we build the function and we focus on the derivative of this function and the preliminary results that help us for future. Okay, but starting Monday, we talk about the integration of these functions. We are going to have a kind of 2 types of integrations. One of them is going to be called line integrals. The line integral is the one that you use in science. And if you want to take, these are all real valued functions. If you want to take a complex valued function, then or complex analysis, use line integrals. Then we extend this line integral at the end into the something that we call it surface integral. So 2 different types of integrals. And at the end, we go back and connect everything to the double integral and triple integrals. Okay, so it's going to be a party of all these integrals really at the end. So that's the idea. Let's do it. Definition first. And it's very important for us to get this definition in order and to understand the objects, okay, the machines that you are going to use. So pay attention, make sure to get these preliminaries, okay, correctly. So what is vector fields? The functions that we're going to interest in. So we have to remind ourselves that what we have and bringing those notations that we did before. So we start with the function that we have, recall that. Okay, I must start with the vector valued function. Recall that a function. Remember the function R, if you like. It's going to be defined on a closed interval A and B. I'm going to R3. That's a vector valued function that assigns a variable t to a vector, that assigns, it's just a machine that we have, a vector, okay, a vector RT R of t to each number, okay, to each number t, which is usually time, number t in the interval of a and b. This is, we know it, is called, okay, it's called a vector valued function. A vector, this is the first one that we study. Vector valued function. Valued function. So the formula for this function is going to be this one, R of t. You can write it down in terms of the coordinate or just vector form, ijk, which is more popular in this part. So it's going to be x of t times I plus y of t times j plus, okay, z of t times k. This is the function that we have, okay, or in vector. So this is the vector valued function that we are familiar. It's the first one that we did. We need this one. Now let's talk about the graph of this function. Remember, the graph is going to be just those space curve. So the graph, that line integral depends on this type of function. That's why we need them. The graph of R of t, you know that we change the t, we get a path. Okay, when t goes through the domain, when t goes through this domain, of course, the domain of the closed interval is, we call it, you know, that is a space curve. A space curve. So that would be, we refer to it, we know it, a space curve C. Each curve would have an equation with parametric. These equations again are going to be quite important with parametric equations. So the parametric equation of your curve are going to be the following. So the x would be x of t, a function of t. Okay, y would be y of t, and the z would be z of t. So that would be parametric equation of the curve. You know that we can eliminate the t, then if you have an equation, that equation would be xy, but the parametric is the one that we are going to use. And you know that these functions are going to be nicely differentiable if the first one is going to be differentiable. So this is the first function that we have. Now, we are, since we are going to work on these curves, so we want to make sure that this is not going to be kind of a constant one. So we refer to the expression of the smooth curve. So we have to introduce that one too, and we keep it for the rest of this chapter. So if R is differentiable, the function, if R is going to be differentiable, such that the derivative of the function, you know that if a function is going to be differentiable, you cannot say that anything about the R prime of t unless you say it. So if R is differentiable such that R prime of t is continuous, because there is no guarantee that if the function is differentiable, the derivative is continuous. But we assume that in this case that it is continuous. So if it's going to be continuous and never zero, because we want to use it for the integral, so we don't want it to be zero, non-zero for all. Okay, for all t in the domain that we're going to have. Okay, if these conditions satisfy, then we say that the C is a smooth curve. It's going to be a smooth all through this, this chapter. C is going to be called a smooth curve. So when we say a smooth curve, you should get to know that this is what we are talking about. Okay. So this is the first group of the functions that we're going interested in. Now we're going to extend it. What we are going to do, we are going to change this t that you get it in this interval, and we change it into the domain in R2 or R3, but we keep the vector part. Okay, so there you are. So let's start in 2-dimensional first, then go to the 3-dimensional. Now, if D is going to be a subset of points in R2, if D is a subset, okay, it's going to be a subset of points in R2, so that we can use 2 variables. Then a vector field, a function, a vector field. Okay, then a vector field, let's say vector field F. Okay, we usually go with the uppercase letters for the vector field. On D, okay, on D is just a function, it's a function that's going to be defined on the D, but the range of the function is going to be in R2 or in R3. So a function, a vector field on D is going to be a function. Okay, so it is going to be a function that assigns, again, that assigns a vector. So the range is a vector f of x comma y, okay, to the given point, to each point. So you drop the point into this domain and you get a vector out to each point x comma y in the domain. Okay, so it's a kind of a function of 2 variables, but it's going to be inside R2. It's not a real valued functions. Okay, so this is what you have now. So this f of x comma y is going to be a vector. It's going to be a vector in R2, of course, it's going to be a vector function in R2. So what you are going to have is going to be equal to, you see, in the case of the R of t, we get x of t, y of t, z of t. But in this case, each coefficient by itself is going to be a function. So we usually use this standard notation. It's going to be m of x comma y is a function in x and the y times I plus n of x comma y in j. Okay, it's going to be a vector. Okay, it's going to be a vector, but the coefficient are going to be functions, since your function is a function of 2 variables. So these are going to be also a function of 2 variables. Okay, so this is going to be a vector field. Okay, is going to be a vector field. Okay, is a vector field in R2 because your domain is in R2. Okay, there. Now we just remind you these components, if you like. Component by itself are functions. Now, what type of functions are these? These are going to be a functions of 2 variables, but they are going to be real valued function. Okay, so these are real valued function of the 2 variables. Okay, so this is going to be the case where m is going to be a function defined on the domain D to the R. Okay, so function of 2 variables, real valued, and the Dn is the same. N is also a function that's going to be defined on the into the R. Okay, this is just extending that R of t and that x of t, y of t that you did before, but it's going to be 2-dimensional. So they are going to be what? They are real valued functions. So m and n are real valued, okay, functions. They are going to be real valued functions in 2-dimensional, in 2 variables, in 2 variables x and y. Okay, so this is the one that you have. So the domain is in R2. Okay, so the points would be x and the y. So it's in the domain is R2. So you have a function of 2 variables. The range is going to be in R2. The range is going to be a vector. So the vector would have a component vector. So the component vectors are going to be functions of 2 variables, but they are real valued functions. Okay, any question? This is in two-dimensional because sometimes you'll be given this in two-dimensional, a function of two variables, but of course in science we are going to be in a space. Okay, so if you're going to be in a space, if you're going to be a space, you are going to get the domain to be, a subset of R3. Okay, so we can go ahead and give you in general. So similarly, if you pick a number, if let's say, if Q, now we get a subset of R3, is a solid if you like, or a set, is going to be a solid in R3 as your domain. Then you are going to have a vector, if you have a vector field, so your vector field would be a function of three variables, okay? So the function is going to be f of x, comma y, comma z. So the domain is in R3, three variables. So the range is going to be in R3 again. So in R3, you have to write them as a, okay, in vector form. Okay, so you need three components. So the components are going to be denoted by m. So this is m function of three variables times I plus n. So that give me x, y, z. Okay, this is going to be j. And then I go with the p, m and p in this course. It's more popular, p. I get a x, y, z, k. You see? This is going to be a vector field in R3. So is a vector field in R3. So this is the most general function, if you like, that you have in this course, okay? And sometimes, we just make these, write down this in short. We just say M and P. And we say M and P, we understand that, those are going to be component vectors of the vector field that we are going to have. Any question? So this is the function that you're going to have in this chapter. This is the function that we are going to talk about, the derivative, integral, etc. Mostly the integration of these functions are popular. So let's give one example. The preliminary examples are evaluation of these. You see at any number that you put for the x, y, z, when you put these numbers, the result is going to be a vector. So if you change your number, you are going to have different vectors. So this means if you move at any point, this would be direct you, if you like. They give you the direction. Those vectors give you direction. You may go to the left. At one point, you come back to the right, left, right, left, right. Okay. These are going to be the type of the function that you have. Let's give one example, then just keep going to get to know it very well. Okay, any question? Just make sure your function, the position of your function, where it's coming from. So you may be, most cases, you may get a two-dimensional one, and you may have the three-dimensional. So, okay, we usually work with the two-dimension, and then we extend it to the three-dimension. This is what we're going to do. Let's give one example to get to know it, okay, to see what is going to be the connections. Quite interesting part. I'm going to give example in a minute, that the way we are going to use it in science, especially in physics. Okay, so the example is you get a couple of these in your assignment. You better do one of them. So they give you something. I do it in two-dimensional with the two variables. Okay, suppose you be given f of x, comma y equal to is a negative yi plus xj. You see, this is a vector field. It's a vector field because you have two variables here, okay, and the range is a vector. So is a vector field. Is a vector field. Of course, a vector field in R2. In R2. Okay, then they ask you to evaluate some of these numbers and describe it if you like. So I'm going to give you some points to show you how we describe this, or what you expect to write when you do those type of problems. So in your book, they ask you to evaluate it and just explain it, but I'm doing it right away. And so they ask for the evaluation of f of 1 and 0. Above 1 and 0, it means you replace the x by 1 and the y by 0. So that gives you 0 here. That would be 0 and the x is 1. So that gives you, I write it down so you know what's the origin of the argument, 1j. So the result would be j. So f of 1 and 0 is equal to the j. So this means if you move, when you get to the point of 1 and 0, you see this is a situation that you are going to have. So this means at the point 1, 0, you see this is the point 1, 0. At the point 1, 0, so your direction would be along the direction of the j vector. You know that the j vector is here. Okay, that's going to be your j vector. So this means your direction is going to be up. If this is going to be 1, for example, so this is going to be your direction here. Okay, this is j. This is going to be the vector j. So you are going to be your vector, your direction is going to be parallel to the j vector. This is the way we interpreted the result. Okay, if you pick another number and you'll be given these numbers, or if you want to see what is going to be f of 0, 1, okay, 0, 1, your x is 0 and your y is 1, so that gives a negative, so negative I. Okay, negative I, x is 0, so plus 0, so that gives a negative I. So this means at the point 0, 1, you see you get to the 0, 1, this is 0, 1, your direction is going to be opposite of the, okay, I direction. You know that the I is, this is the I. Okay, this is going to be the I. You have the negative I, so we get another direction. So if this is going to be a kind of a 1 again, or the negative 1, so you go in this direction when you start with, starting at this point. Okay, so the graph of these are going to be like, you see, you get a collection of these format that you're going to have. So that's why we call it a field, like electrical field, if you like. Okay, gravitational fields. So it's going to be the same thing, if you want to pick another number, another point, and the next point is a negative 1 and 0. If you put the negative 1 and 0, x is equal to negative 1 and y 0, so that gives you 0, and that gives you minus j. So this is going to be equal to the negative j. So this means if you get to the negative, the point in negative 1 and 0, this is going to be negative 1 and 0, and the direction is going to be opposite of the j again. So the j is going to be this direction, so your direction is going to be opposite, so you're just going down. Okay, and then you can continue forever. And one more point is like f of 0 and negative 1. Okay, your x is 0 and y is a negative 1, so negative will be positive. So it's a negative 1 times I plus 0, so that gives you I. So this means at the point 0 and negative 1, okay, at this point, your direction would be, you go as the direction of the I. So that's going to be the direction of the I. You see, so it's just moving around in different format to get a collection of these fields, if you like, okay, the format. Okay, so this is how this function would behave. But we have 3 famous vector fields, and all these going to be applied to it. And I just remind you those 3 that we are going to use it. So, if you want application type problems, it's going to be from these. So one of them is just a moving object. It's going to be velocity field. Okay, we have a velocity fields. You see at this direction, you have a different, when you move with a different velocity, different speed. This is the first one. The other one is gravitational one, gravity. Okay, that is gravitational fields. It's very popular. And the last one that we consider are going to be electrical fields and electric force field. Force fields are, are popular examples, are going to be examples. Okay, examples of vector fields. So if you want to discuss the property of these fields, you need this chapter. And we get help from time to time when you want to, when you want to justify something, we say, oh, from gravity. And we use some expressions that's going to be related to the physical application of these quantities rather than the abstract. Okay, so these are going to be the objects that we're going to have. We call them vector fields. We don't usually use the function term. So this is the first one. Any question? Now, there is one example of these vector fields, which is going to be our very important tool. Okay, so we are going to introduce it right away, and that will help us quite a lot to get a kind of, you see, there's going to be a calculus of this part. So this function would help us to copy whatever you did for the calculus of one function of one variables to these type of functions, okay? And that is nothing but remember gradient, the gradient vector example. The example is that the gradient, okay, if a function f is given to you, the gradient of the f is always a vector field. And that's quite interesting. Okay, so the gradient, you must know it. The grad, okay, the gradient of any function, of a function f, okay, is always a vector field. Is a vector. This is one way to make a vector field. You see, you say, oh, you give me a function, I make a vector field out of your function. You give me ordinary function, then I make a vector field for you. Okay, and you know that the definition of the gradient was what? Remember, the gradient is this one. That's it, the grad of f, remember? The grad of f was a vector. Was a vector with the component was partial of f respect to the x, partial of respect to the y, and partial of f respect to the z. You see, this is a function, and the range of this function is a vector. You have the vector here, and these are going to be those component vectors that you are going to be interested in. Okay, so for example, it depends on the function. For example, if your function is going to be f of x comma y, you give me this function as x squared y cubed minus 3xy. If you give me this one, I can quickly make I can make a vector field for myself or for you. Okay, so the way we do it, just we consider the gradient. If this is going to be the case, then what is the gradient of this function? The gradient of this function is going to be equal to, you know that you are going to get only f sub x and the f sub y, the partial. So this is it, the partial respect to the x, the derivative of x squared will be 2x, so that gives you 2x y cubed. Okay, and the partial respect to the x, that give you 1. So the partial respect to the y, that give you 3y squared. So it's going to be 3x squared y squared. And over here, respect to the y, that give only negative 3x. That's it. You see, as you can see, this is a vector field. It's a function of two variables, each component. So this is m, this is n. So this is going to be is a vector field. Is a vector field in R2. Okay, so it's one source of making or providing the vector field going to be gradient of the function. Any question? Now, that will take us to our first very important question for the rest of the course. And the question is going to be, see, Over here, if you consider a function, a real valued function of the 2 variables, 3 variables, then I can make quickly a vector field for you. Okay. So the question is going to be, is this the only source that you can find vector fields, or there is any other source? So is this any source means if you give me a vector field, can I find a function like this so that my vector field would be the same as the gradient of the f? Okay, so this means this is going to be a kind of a general rule for finding all the vector field. So this is a very important question to consider. Okay, so what's the question? The question, remember, if you have a function, the gradient of that function would be a vector field. So the question is, if you have a gradient, if you have a vector field already, can you write that vector field as a gradient of a function? So this is going to be a question. If f, okay, if f is a given vector field, can one find, if you like, or we find, can one find a function f, a real value function, okay, such that the gradient of the function is going to be the same as our vector field. So later on, you will find out this is going to be the key in order to talk about the integration of these functions, if you can find it. So that would be the best, the best thing. Of course, in general, you may not be able to find it, but if you can find it, in a minute, we are going to give it a condition that make it possible for us. If you can find it, that would be a great advantage for your function or your vector field. In that case, we are going to give a name to that vector field. This name is coming from physics. So in that case, we say that our vector field is conservative vector field. Okay, conservative. The first time that you say conservative, you may think about conserving energy, etc. And then you will see later on that it's not going to be irrelevant. It's very much relevant to those type of idea in physics. But for the time being, we just borrow the name and then we work on it. Okay, so, and that's an important question. So to answer this is mathematics. Okay, if you want to answer this question, you assume that this is true, then you go to see what condition would, what condition do you need to get this one? And that condition, you come back and you say, oh, if your function would have this condition, then it's going to be true, okay? So if this has happened, we are going to make a definition first, and then we investigate it. When are we going to get it? Okay, of course, the answer is not all the time, but we get it most of the time. So how are we going to get it most of the time? We are going to show you. Okay, any question? Keep in mind this one, and that will take you to the end of this course. Quite interesting. So we make a name for it. If this has happened, nice. We say we have a conservative vector field. You have to know this expression through the course, through this chapter. So what is a conservative? Okay, what is, it's, as I told you, it's going to be related to the energy. What is conservative? Conservative vector fields. Conservative vector fields. A field is conservative if we can write it down as a gradient of other function. Okay, so there you are. A vector field. A vector. So if that answer is positive, it's going to be the one. If a vector field, okay, a vector field F is called It's going to be called a conservative field. Conservative. Okay, conservative vector field. So that's the expression, get to know it. Okay, it's going to be called a conservative vector field if we can find a second function. If there is, okay, if there is a differentiable function, there is a differentiable function, real valued function. Function f, okay, a function f such that the gradient of this function is the same as your vector field. Means if that answer is positive, okay, if your, this means, you know, it's going to be conservative, you have already got the shape of your function, if you like, that your function is like a gradient of another function. If this is going to be the case, we have a special name for this, and we call this one potential function. And again, later on, you would find out it's related to the potential energy and, you know, kinetic energy, and you put them together, you have something, you know, we call it, I think, conservative principle or something. So you will see them, that we prove all of them. Okay, so in this case, we know this name that we have. Okay, see if I can get another over here. Okay, so this is it in this case. In this case, you have to know this name. F, that function is going to be called, a potential. Okay, a potential field, potential function. Potential function. Okay, potential function of the vector field f, of the vector field, okay, vector field f. Maybe we're going to do it. Okay, so that would be the case. Now let's say what is the condition to get it? Because a function would be given, a vector field would be given to you. And your first job in this chapter is to check to see if it's conservative. If this is going to be conservative, then they ask to find the potential function. Because in a process, you have to find the potential function. But sometimes you may have to try it first to see if it is the case. If you want to do it, let's do a little of algebra. Let's open up this equation, form it, to see if we can get a condition that will help us to be able to do it practically. Okay, so I'm going to expand this one to see if I can get something to remember. So note that. Let's introduce this function. Okay, note that if I go with the vector field in R2 first, then I generalize it to the R3 because they are going to be different. So if you are going to be in R2, so f of x comma y, remember m and n is going to be m of x comma y I plus the general term of the vector is going to be n of x y comma j. So in short, we write it as m times I plus n times j. Okay, this is going to be your function. If this is going to be the case, and f is conservative, and f is equal to the gradient of the f. So let's form this equation. So this is in vector form. This is going to be what? And this is m comma n. And in vector form, this is going to be what? This is going to be partial of f respect to the x and the partial of f respect to the y. Okay, so if they want to be equal to each other, they are two vectors. And you know that the vectors are going to be equal to each other if their components corresponding coordinates are going to be the same. Okay, so this means f sub x must be equal to the m. Okay, so the conclusion is f sub x equal to the m, and f sub y must be equal to the n. Do you get it? Okay, now let's go a little bit more. So this means in practice going to be round f round x is equal to the m. Okay, let's differentiate respect to the y. If you differentiate respect to the y, so that give a round y of the round f round x. Okay, so this simply would be round m over round y. So you know that this will give you the second derivative, round 2f over round y round x. And now this happened to be round m round y. Okay, so open up this one. So in this case, we have a round f round y is equal to the n. Now differentiate respect to the x this time. If you partial it in respect to the x, so this is going to be round f round y, and this is the round n round x. So this would be the second derivatives, round 2f, and the round x round y, and this gives you round n round x. You see, that's it. You know that this is giant, those f21, f12. So if you assume that the partial derivatives are continuous, according to the theorem, remember the Clairaut theorem that we did have before, and the order is not going to be important. The order is not important, so this means the first one and the second one are going to be equal to each other, okay? So we assume that if the partial derivatives are continuous function, that was the condition of the theorem, are going to be continuous, then you see fxy is equal to the fyx. And that's exactly what you got over here. Okay, so if these two equal to each other, so this means the other part must be equal. So that give a round m round y is equal to the round n round x. That's it. Or in short, this is it. My is equal to the nx. This is going to be the condition that you need to make sure that your function is conservative, your vector field. If you have done a differential equation, remember in a differential equation of the form of, they are related to each other, mdx plus ndy equal to the 0. That differential equation is exact if this condition satisfy, and they are related to what we did over here. So that will help you a little bit to connect. But they borrowed it from here, a more general case. Okay, so what we did, we find a tool, we find a test. So if a vector field is given to you, and we are very much interested to see if that vector field is going to be conservative, we're just checking this condition. Okay, we're checking this condition to make sure it's conservative. And if this is going to be conservative, then we can use this equation over here to find the potential function. And this is your job most of the time in this chapter. Okay, so I'm going to make it official because the one that I did, I just proved a theorem for you. Okay, any question? So let's make it official. Officially, this is going to be, we call it a test, if you like, to see if something is conservative. So we prove it, we can call it a theorem because we proved it. Okay, theorem, we can consider this one as a test for a vector field to be conservative. Okay, for conservative vector fields, of course, in R2. Conservative vector fields in R2. Okay, so that's it. The function f of x comma y, which is equal to the m times I. M is a function, and the nj, as we talk about, is the conservative, is a conservative. Is going to be a conservative vector field. Okay, conservative vector field in R2. Okay, if and only if this condition satisfied. The condition is round m round y is equal to the round n round x. That's the one. Okay, in short, if you like, or that's easier to remember. M sub y is equal to n times x. That's it. That's a condition for the two condition for the vector field in R3 is a little bit different. And we do it, if we do it later, we do more of them. But first, we just stay with this one. And then we come back and we do the other one too. Okay, any question? So this is the first thing that you have to remember, the test for the, of course, you know that this partial derivative must be continuous. So you can say that I have to add that condition because I used it. Okay, of course, when the partial derivatives are continuous. When partial, because you need that continuity to make sure that the order is irrelevant. Okay, when the partial derivatives, okay, when partial derivatives of m and n are, of course, continuous. Okay, we assume this continuity all over the case that we have. Okay, so this is going to be our main job. So we give an example to do it for the two variables. Okay, to get to know it. Any question? Are you ready to do this? That's it. Again, if you have done differential equations, it's the same thing that you do. When a differential equation is given to you, you want to check to see if this is the exact equation, and the exact equation would be this condition. It's going to be related to the conservative. Okay, example. A function would be given, a vector field would be given. They ask you to check to see if it's conservative. And if it is conservative, of course, then you have to find the potential function. Remember, the potential function is a lowercase f, because this is going to be equal to the gradient of a real valued function. Then you have to find that function for us. Okay, but we test it first to make sure that it is the case. Okay, you have quite a lot, and you are going to do it quite a lot. Just make sure to pick a couple of them from your book, because you need them for the next quiz. Okay, so let's check. We give you a couple of them because there are some techniques that we have to check. So we want to determine if the function, determine whether, okay, whether or not, this expression for your book, whether or not the vector, okay, the vector field is conservative. Means if this condition satisfied. Then if so, if your answer is positive, go and find the potential function. If so, find a function. Find a function, function f, real value function, such that the gradient, your vector field is going to be equal to the gradient of the f. It's the way your book explain it, but we usually say that it's like this, or just find the potential function. So just get to know it. We may give you this expression, potential function. Okay, it's the same thing. Okay, are you ready? Let's start with this one. The function is f of x, y is equal to what? Is x minus y times I plus x minus 2 times j. This is your function. Okay, its function is R2. Just use our notation going to be standard. So this is the one that you have to call it M, and this is the one that you call it N. Okay, so solution, you get M and N, and you check this condition. That's it. So M is equal to X minus Y. You see, M is the first component, but you differentiate respect to the Y. So you find F sub Y, the with respect to the Y would be -1. That's the first one. Then we get the N. N is X minus 2. That's the second component, but you differentiate with respect to the X, that give you 1. As you can see, they are not equal to each other. So this is M sub Y is not, sorry, that's N. That's NX. Okay, NX. Okay, M sub Y, partial derivative with respect to the of M respect to the Y is not equal to the NX. So the answer is no. F is not conservative. Okay, so that's the first type, or the case 1. Any question? So let's check one that it is. Okay. So how about having a positive answer? Case 2. Okay, case 2, the function is, this is the function f of x comma y equal to, your function this time is 3 plus 2xy times I and plus x squared minus 3y squared times j. This is your function. Again, this is your M. This is your N. Bring them down and check it. Okay, so our solution is going to be M is a 3 plus 2xy. Differentiate with respect to the y. M sub y. If you have 3 0, derivative of y is 1, so that gives me 2x. Okay, that is going to be my. Then we check n is equal to the x squared minus 3y squared. So we check the n respect to the x. That give it 2x. So that would be the case. So M sub y is equal to the N sub x, and the answer is yes. Okay, so F is conservative. Okay, it's conservative, so now you have to find the potential function. Since it's conservative, so this means you have to find a function, remember? You have to find a function which satisfies this condition. The gradient of the function must be equal to your f. And this f is missing. Okay, you form the equation, use this information to get it. So the function is in R2, so your gradient would be f sub x and the f sub y. And the potential function is, sorry, the field is Mn. So you are going to have a system of the equation. F sub x is equal to the M, and the f sub y is equal to the n. You are looking for the f, remember. So form it. So this means f sub x is equal to the m. M is 3 plus 2xy. F sub y is equal to the n, and your n is x squared minus 3y squared. Okay, so from this system, you have to integrate to get the f. You have two choices, of course. I'm going to call this one 1 and 2. So you can use one of this equation to integrate. Both of them are going to be the same. If you pick the first one, you have integrate respect to the x, partial integration. Integrate respect to the x to get the f. If you take this one, you have to integrate respect to the y. Sometimes one of them is going to be easier. In this case, both of them are going to be the same. But the catch is, when you integrate, there is going to be a constant. If you pick the first one, you keep the y constant. So your function, your constant must be maybe a function of y. Then you have to try to see if what is that function. Use the second one. If you use the second one, you integrate respect to the y. So the constant will constant. So it's going to be the procedure that it takes time to find it. So I'm going to start with one of them. Doesn't matter which one is it. I start with the one. Either one is fine. I start with the number one. In number one, I integrate respect to the x, both sides. So that give me f of x comma y. I write it down so that you know what's going on. So I'm going to get the partial integration respect to the x. So that give you the integral of a 3 would be 3x. And respect to the x, that give it 2x squared over 2. I write it down for you. It's going to be 2x squared y over 2. But there is going to be a constant. Since you fix the y, so your constant can be a function of y. You see, g of y is not a constant c, because your constant is going to be, and your job, we just simplify these two. So this is going to be 3x plus x squared y plus g of y. So you have to find the g of y. Okay, so the next question is going to be, what is g of y? Any question? To get the g of y, we are going to use the second equation. So what we do is, this is so far is the f function. So we differentiate it to find the fy, and then we put the fy here. Okay, so this is it. So I'm going to differentiate this one. I give you f of y. F of y, derivative of the 3x would be just 3. And the derivative with respect to the y would be plus, say that's going to be f. I differentiate with respect to the y. I'm sorry, derivative with respect to the y of the 3x would be 0. That would be 0. Respect to the y, that give you x squared, and I have a g prime of y. Okay, so f sub y is equal to the x squared plus g prime of y. I call this one equation number 3. So what I'm going to do, I'm going to drop this one in the 2. Okay, so I'll go back to the equation number 2, and I substitute fy. I substitute fy to be x squared plus g prime of y, and this is going to be equal to the x squared minus 3y squared. Okay, now as you can see, the y x squared and x squared will cancel out. So I will end up with g prime of y equal to the, okay, so I get the g prime of y equal to the negative 3y squared. So I integrated to get the g function. Okay, so that would give me integrate. That give me g of y is going to be equal to the minus, that 3y squared would be 3y cubed over 3. Okay, it's going to be 3y cubed over 3 plus the constant c now. 3 and 3 would cancel out. So g of y is going to be equal to the negative y cubed plus c. That's it. So go back and substitute the gy here. That give you your function. Okay, so I go back. So the final answer is going to be, so f of x and y is equal to, I have the 3x plus x squared y plus g of y. We need one of these solutions. And you can add the constant c or not, it doesn't matter. So this is going to be your function. We don't usually write the c because we need only one function would be enough to get this true. Okay, so this is going to be the potential function, if you like. One of them is just f of x, y is a 3x plus x squared y minus y cubed. So this is going to be a potential function for, for your conservative field that you start with. Okay, any question? You do this one exactly again in that course, differential equation. When it's exact, then you go back and you find it. And the way we do it over there, this would be the result of the differential equations. But over here is different because we connected to this conservative force. Okay, this is going to be the case 2. Any question? So that would be case 2. I give another one, then I give a break. So we finish it. Most of the time you have a trigonometric one, exponential one. We just want to make sure you feel all right to do it. Okay, so that's a number 2. Number 3, you see in this one, I integrate the first equation and I work on the second. So the constant was a function of y. So you may start with the second one. Your constant would be a function of x. So I try to do it with the second example, or the third one, so that you know the possibilities. That's why I wanted to give you another one. Okay, let's see. I do it the other way around so that you have all the possibilities. And so what is the vector field? This is your vector field of x comma y is equal to the e to the x sine y, okay, times I plus e to the x cosine y times j. This is your function. It's in the complex analysis, you change this one, the function, we write it down in terms of the complex variable. It's very similar. It's e to the z. But we stay here, and this is it. So this is your m, and this is your n. Check the condition first. Solution. M, I repeated, e to the x sine y. Differentiate respect to the y. Okay, only cosine y here. So my e to the x cosine y. Okay. The other one, n. Your n is e to the x cosine y. You differentiate respect to the x. If of e to the x is just e to the x. So that gives you e to the x cosine. So they are equal to each other. So yes, f is conservative. Okay. So the next question is going to be, where is the f? So you need to find the function f so that the gradient of the f is equal to your function. And the f is missing. Again, form that equation, see definition, partial f respect to the x, partial y, and this is going to be your mn. So form those, that let them equal to each other. The first one would be f sub x is equal to the m. What's the m? e to the x sine of y, f sub y is equal to the n e to the x cosine of y. That's your equation number 1 and number 2. Again, you have to integrate. Okay, you start with integrating the first one, the second one. Both of them are the same, but I do the second one first. I want you to see the second possibility, second option, but you can do the first if you like. But I do the second. Okay, so from the second one, I integrate respect to the y. So give me f of x comma y, integral of e to the x cosine y dy. Okay, so the x is constant, derivative integral of a cosine is just simply sine. So that gives e to the x sine of y. But this time, you see, the constant, you keep the x constant, so you are going to have g of x. Okay, we get the g of x because that's constant, so you have to find the g of x. To find the g of x, we are going to use the first one. So we differentiate respect to the x. So that gives you f sub x. Okay, f sub x would be simply derivative of e to the x is e to the x sine of y at plus g prime. Okay, this is going to be your equation number 3. But you drop it into the 1. So you go to the first equation, okay, you substitute, or you let just 1 and 3 to be equal to each other. So the conclusion is going to be what? It's going to be e to the x sine of y plus g prime of x is equal to the e to the x sine y. So this 2 would cancel out. We get nothing because g prime of x would be 0 and the g of x would be constant. So not a big deal. So your function is going to be f of x comma y is simply e to the x sine y. Okay, e to the x sine y plus a constant c. So that gives you the potential function this time. Okay, so sometimes it's important to pick a correct to start with, but most of the time they are kind of polynomial types. We have nothing to worry about it. Okay, any question? So it's 12 o'clock. We give it 10-15 minutes break. We come back. This is a function of 2 variables. You have to check the condition for the function of 3 variables. And that's the one that we are going to be getting involved. Not difficult, so the algebra is a little bit more involved. Again, we have to test it. We find the condition, and then we come back and we do the similar problems. But this time, the function is going to be a function of 3 variables. The way you are going to use this in future are going to be quite interesting. You see, when we introduce a notion of integration for this type of function, then in the case of the function of 1 variable, remember you have fundamental theorem of calculus, which means if you want to find the integral, you find the antiderivative first, and then you substitute. Remember, integral from a to b f of x dx is f of b minus f of a. When we get to integration of this vector field, if it's going to be conservative, we change it to this one. And this would be like the f prime in a course of the function of 1 variable. So that will help us quickly. If it's going to be of this form, like calculus 1, f of b minus f of a, and we're done. Of course, when we put the definitions together. That's why it's a key concept to this argument. Okay, so let's have a break. We come back and we try to finish these preliminaries. We have those 3-dimensional, this is the only one that we have. Okay, see you then. Okay, so we are going to continue to see what is going to be this definitions in the case of the function of three variables. Okay, so in order to get through it, we need a new definition. Okay, it can be done. You can, you can use the the same idea over here. The integration takes a little bit more time, but in the meantime, we are going to introduce a new term that we're going to use in future. Okay, so the new terms that we need, it's going to be called curl of a vector field. You are going to have two great theorems in future, Stokes and the Green theorems. So we need this type of expressions. So what's going to be curl? Okay, curl of a vector field, a vector field that we take as to a condition for the vector field to be conservative in the case of the three variable. So we have a differential operator that we used before. We are going to repeat it again. We call it the del notation. Okay, del notation. I introduced this one before, or differential. Okay, or differential operator. Operator notation, this is the one. Use it for the gradient before. And this notation is defined as, it's going to be partial derivative notation. Say partial derivative, respect to the x, respect to the y, respect to the z. Okay, for example, in the case of the gradient, if you have the del of f, that was the partial derivative of the f, respect to the x, respect to the y, respect to the z. So whatever you put over here, you are going to get it here. In vector form, it can be used in this format, round x I. So it's going to be round y j and round z k. It would be helpful to have this notation. Now let's consider a vector field in three-dimensional. Okay, so if you have a vector field in three-dimensional, f of x, y, z is equal to, so you are going to have m, the first function times I, second function n times j, and the third function I go with the p times k. So m and p, they are all real valued function of three variables. If this is going to be the case, then the curl of f, curl of f is going to be defined by, this is it, curl of f is equal to, is going to be that operator notation, if you like, differential operator, that's cross f. Okay, cross f. You know that the cross product would be what? The cross product would be a vector and would be defined by the, remember, by a determinant of a matrix. So this is going to be the definition of the curl. So the curl of f is going to be equal to determinant of a matrix. Remember, ijk, I, j, k. Then the first vector, differential operator, so that's going to be rho x, rho y, rho z, and this is going to be this is going to be f. So the f is, the first component is mn, so this is it. M, N, P. This is easier to memorize it in this form. When the function is given to you, form the matrix and then find the determinant. But if you don't want to memorize it in this, so you have to find the determinant of a matrix. And this is going to be the determinant. So it's up to you. What is going to be the curl of F is equal to, remember, this is going to be ijk. So it's going to be I, you eliminate the first row, the first column, and you get this one. Okay, so you get the round P. We compare P and the round P, round Y minus round N, round X times I. You see, this is the way we write it down. It's easy to memorize it. You see, this is the first component. The first component is M. You just delete the M. So you compare the P and the N together. P is P and N. Okay, P and N. So P is this last one that we have over here. So that would be round P. This must be something wrong. Let me just check. This is X, Y, Z. So this is Z, sorry, Z. Z. Okay, as you can see, N is the second component, the Y, and this is the third one, the Z. So we do it the other way around. That's going to be round P, round Y minus round N, round Z. We compare the P and the N together. Then it's going to be minus J. And then with the first row, second column, you compare the P and the M together. So it's going to be round P, round X minus round M. P is in the Y position, Y, times that by J. Okay, plus the last one. So the last one, you just eliminate this. Okay, you are going to compare P and N together. This is it. M and N. So it's going to be round N, round X, minus round M, round Y, times K. This is the formula for the curl. Okay, it's easy to remember the way you compare them together. You see, look at this one. The first component is M. You drop the M, you compare the P and the N together. So P was in the third, you see, in the third position. So round P, round Y. Since you compare it with the N, round Z, coming from the P. The second component is N. You drop the N, you compare the P and the M together. So round P, M is in the first position, round P, round X, round M, round Y, because of the P. The last one, you drop the P, you compare the M and the N together. So it's going to be N, round X because of the M, and the round, it's just, you can bring the formula, to the test, but it's easy to memorize it. Okay, so as you can see, curl of F is a vector. You see, this is going to be just, in general, is going to be a vector field, because this is going to be the function that you have. Okay, by itself is going to be a vector field to get these numbers. Okay, any question? You should be able to find it. A couple of places that we need it. So let's see what is going to be the case. If you want to see what was going to be geometrical interpretation of this one, you can think about the, okay, if you have a liquid like a coffee or something. So if this is going to be the one that you have, okay, at one point, if you get this point, and this curl give you the direction that, if you get a coffee, and if, this is going to be the coffee going around or any liquid, so that give you the curl. give you the direction of the liquid at any time. You know, this is a kind of the way you are going to have these liquids to bend, if you like. They call it the curl of the of the vector field. So let's find it. A function would be given to, then you have to find the curl for us. You have the formula and you get the result. Okay, let's do it. Any question? So let's have one to get these numbers done. Shouldn't the second group be round P round X? Oh, that's Z, it must be Z. Yes, you are right, this is Z, sorry. Z. Because you compare together, you see P is in the Z position, so PZMX, PN, PZNY, NM, NY, MX. This is the way you are. Very good. Okay, so let's do it. So you're going to have a function and you have to find it for us. Just make sure this is one of those formulas that you have to have it. So one example, then we come back to the question of the conservative field. Of course, this is the one that we are interested in. So example, we wanted to find the curl. Okay, find the curl of the vector field. Vector field. This is your vector field, f of x, y, z, which is equal to the xz times I plus times x, y, z, x, y, z times j minus, okay, minus y squared k. So that's the one. Okay, you know that this is going to be your m, n, and the p. Quickest way to do it is just a matrix form. You don't have to memorize anything. Curl of f is equal to matrix ijk, I, j, k, derivative respect to the x, derivative respect to the y, and the derivative respect to the z. Function m and p. M is x, z, n, x, y, z, and the negative y squared. Okay, to find it is equal to the I times cross multiply, you see, derivative respect to the y minus derivative respect to the z. Derivative of the negative y squared respect to the y would be negative 2y minus derivative respect to the z would be xy. That's the first one. Any question? Minus j times. So eliminate this one, so you get these two. Derivatives respect to the x, there is no x, 0. Derivative respect to the z, x times j. Okay, that's the next one. This is the last one. So eliminate the first row, last column. Derivative respect to the x. Derivative respect to the x would be yz minus derivative respect to the y. There is no y here. So it would be 0 times k. So the curl of f is going to be equal to, there you are. You get the negative 2y minus xy times I, negative positive plus xj, okay, and plus yzk. This is the curl. Okay, this is the way we find it. You don't have to memorize the formula, really. Any question? So it's going to be just a vector field at different points. You get the direction of the fluid, if you like. Now we come back to the question. The question is, if one of these functions would be given to you, how are you going to find out that this function is going to be a conservative vector field? The idea is the same, okay? But we would like to get the condition. So what condition are going to impose to make sure it is, okay? So we get the question and we are going to answer it for you. So what is going to be the question? Question is, if the vector field in R3 is given to you, how do you find out that this is going to be a conservative one, okay? So if a vector field, again, we wanted to see it, then we give you the formula. If a vector field f of x, y, z is given, then, okay, then it can be proved. We answered the question. It can be proved that f is conservative. F is conservative, even only if the curl is equal to the 0. The curl of f is equal to the 0. We can prove it for you. Okay. If you want to see the proof, note that if f is conservative, at least we can prove one side for you. Then, if it's going to be conservative, you know that then there is a function, potential function. Okay, then there is a function f such that the gradient of the f is equal to the f. You know that this is the definition of the conservative. I want to prove that the curl of the f is 0. So what is going to be the curl? Okay, in this case, curl of the f, remember the curl is what? So the curl of the f is the same as the curl of a gradient of the f. But what is the curl? Remember the curl of the function is going to be del cross the function, del cross del of f. Okay, when you write it down, you know, it's like those format that we did have before, like the cross product with the same kind of row, then it's going to be 0, but we can check it. Okay, so it's just a definition of the curl. So what is this? This is going to be equal to the vector, the matrix. This is going to be I, this is going to be J, and this is going to be K. The first vector is the del vector, so it's just partial respect to the X, partial respect to the Y, partial respect to the Z. That's a first vector. The second one is a gradient of the F, which is F sub X, F sub Y, F sub Z. You see? If you find this determinant, that gives you 0 right away. I'll just show you one of them. You see, this is going to be equal to the first one. You eliminate the first row and the first column. Look at this. You already got the F sub Z. So you differentiate respect to the y. So that give fzy minus, that give you rond z fy. So that give you fyz. But you know that these two are equal to each other. That give you 0. It's the same for the others. Minus the second one. If you eliminate this column and the row, that give you fzx or fzx minus that give you fxz, which is 0. And the same for the other one. That's the last one. The last one give you fyx minus fxy times k. This is 0. You know that the second derivative, you have no order for it. So curl of f is equal to the 0. Okay, you know, this it would give you the result. I'm going to write on as a theorem. I just wanted to say it so that you believe it. So for the function of for the vector field in R3, if you want to check to see if that is going to be conservative, you have to prove the curl is 0. But what would happen if the curl is 0? Look at this one. That's a curl vector. If this vector is going to be 0, then the component must be 0. So if you put this component equal to 0, that gives you 3 equations. You see, py equal to the nz, px is equal to the mz, nx equal to the my. So you have a system of 3 equations, and you can use it in order to find your potential function. Okay, so this is the one that we are going to be interested in. So this is going to be the test for the vector field on R3. Vector field to be conservative, of course. So our argument would be summarized on this theorem. And you are going to use both of them when we get to the notion of the integral. So this is going to be test. You need these two form of test for a vector field in R3 to be conservative. Or a vector field okay, in R3 to be conservative. Conservative. That's it. So we already proved everything we need. We just write it down officially. Suppose M, N, and P. We know that where they are coming from. Component vector of the vector fields. Component function. Suppose they have continuous partial derivative. You need continuous partial derivative so that you'll be fine with this. Okay, regard to the order of the second derivative. So suppose they have continuous, have a continuous partial derivative, partial and derivatives on the solid, the domain. Solid Q in R3. If this is going to be the case, then the vector field, f of x, y, z, which is equal to the m times I, n times j, and the p times k. is conservative. Conservative. Okay, it's going to be conservative if and only if and only if the curl is equal to the 0. This is the one we already talked about it. And this means if and only if they satisfy this condition. You see, the condition is very easy to write. You have three functions, you compare them together. You see M and P. See, this is the way you can, you can bring it to the test, but it's the way easily you can compare, you see. I want to compare M and the N. So I should have the round M. Since I want to compare it with the N, it's going to be round MY. Must be equal to the round NX. That's the first condition. Then I want to compare M with P. M and P. M is in the X position and is at the Z position. So round M, round Z is equal to the round P, round X. That's the second one. The third one, I compare the N and the P. N and the P. So round N, P is in the Z position. Row Z is equal to the round P. N is in the Y position. You see, that's a 1, 2, 3. It's very easy to remember these conditions. Okay, any question? And we just find it from, this is it. You let this one to equal to 0. You get exactly what I did. Because all these components must be equal to the 0. All these components must be equal to the 0. And if you let them equal to the 0, you get exactly what I did over there for you. Okay, this is the M and the N. You see X, Y. M and the P, X, Z. P and the N, Y, Z. But you just bring it to the test. So we are ready to test it. Okay, everything we did was to be able to solve this problem and we finish it. Because as I told you, we want to integrate. We don't integrate really when we get to those vector fields. We just check to see if they are going to be conservative. As soon as they are conservative, we find the potential function and we use a like of fundamental theorem of calculus or of integral to do the job. That's why that makes it so interesting to check this one all the time. Okay, little bit up. This is it. Okay, so that's why they are going to be interesting, key to what we are going to do in future. We just integrate we do the integration if the force is not going to be conservative. Otherwise, nice, the complicated one, all of them can be done with these formulas, but you have to find this potential one. That's your main job. Okay, let's do it. It takes a little bit more time because you have the system of 3 equations to check. So I'm going to go, are you done? I'm going to the next page, and this is your main job. You have 2 jobs, just one, to find this potential function, but you find it in 2 cases, a potential function in 2-dimensional and 3-dimensional, 2 variables and 3 variables. We don't need anything else from this section. So let's do it. That's it. So we want to show that. You have quite a lot in your book. You better look at a couple of them in this section 15.1. You have quite lots of problems. Just make sure you are familiar and you can do it quickly because it takes time. Okay, there you are. This is a vector field. X, Y, Z is the first component is e to the x cosine of the y plus y z times I. The second component is xz minus e to the x. Okay, e to the x sine of y times j. And the last one is xy plus z times k. This is the vector field. We want to show that it's conservative and find it's okay, show that is conservative. Is conservative over its domain, which is R3. Okay, over its domain, and of course find a potential function. Okay, and find a potential function. Function for this vector field. That's it. Okay, they ask you to show, so we check the condition first, and then we go for it. So you know that this is going to be the standard notation that we use, M, N, P. So bring them down here because you need them. Okay, so your M function is e to the x cosine of the y plus yz, that's M. N function is xz minus e to the x sine of y. And your P function is xy plus z. Compare them together to get this idea that I talk about it. So I compare it in this direction that I have. I compare the M and the N together. So I have to have the round M. N is y. Should be equal to the round N. I compare with the X, which is M, which is the X. Okay, X, Y, Z, if you like. The components, the composition. So check this one. Round M and round Y, derivative with respect to the Y is going to be what? Is a negative e to the sine of y and plus z. This must be equal to the round N, round X. Derivative with respect to the X, that gives you z. Respect to the X, you just derivative of e to the X is e to the X minus e to the X sine of y. So the first condition is satisfied. Okay, any question? Second one, I compare the M to the P. So I should check round M, the P is in the Z position. Round the Z is equal to the round P, M is on the X position. So that's it. With respect to the Z, this is 0, respect to the Z that give me Y. With respect to the X, if of X is 1, Y. So that is satisfied. Okay. So the last one, I compare these two together. Okay, I compare these two together. So I have the round N, P is in the Z position, and this is going to be round P, N is in the Y position. With respect to the Z of the N would be just X, and the derivative of the P respect to the Y would be just, okay, X. So yes, it is conservative. Okay, so F is conservative. So this means we should find the, okay. So we should be able to find the function F. Okay, so the next step is going to be finding a function F that satisfies this condition, and the F is missing. Potential function, you know that. Now go for it, the function, a function of 3 variables. So this would be F sub X, F sub Y, F sub Z, partials. And this is M and P. Let them equal to each other, and then get the system of three equation, three variables. Okay, so we start with the m sub x equal to the m. So the system would be the partial of f respect to the x equal to the m. M is e to the x cosine of the y plus yz. Okay, so this is m. This is, these two together. Like likewise, this would be equal to the n, and n is xz. Okay, xz minus e to the x sine of y. And the third one is f sub z is going to be equal to what? This must be equal to the p, and the p is this one, xy plus z. You see, you have three equations, 1, 2, 3. So you have to pick one of them to start with. You start with integrating one of them. When you're integrating, you have two variables fixed, so you have two constant, if you like. So that constant part of the integration would be a function of two variables, and then you have to check, whether that should give you anything or not. Okay, just have a look to see which one is going to be easier. It's no big deal, because if you differentiate respect to the x, this is just e to the x, stay the same. So I'm going to start with the first one. Okay, so from the first part, I integrate to get my function, so I have to integrate respect to the x. So the function, which is going to be in this case three variables, x, y, z, is going to be partial integral of e to the x cosine of the y plus yz, but integrating respect to the x. Okay, respect to the x, this e to the x would be just e to the x. Okay, so that gives us e to the x cosine of y. But this considered as a constant, so we consider this one as a 1. If the integral of 1 would be x, so that gives you xyz. xyz. But you are going to have a constant. But you have a constant. You have a function of the constants, g. So you integrate respect to the x, so your constant can be y or z. Y or z. Okay, so that would be the first part. But you have to check what is g. So the next step is going to be what is g of z. Any question? Now, to get the g of z, you have to check it in 2 and 3. You check it in 2 to see if there is any y, and you check it in 3 if there is any z. So to get the 2, you have to differentiate this one respect to the y. So find f of y. So derivative respect to the y. Respect to the y, derivative of a cosine is a negative sign, so that gives a negative e to the x sine of y. And derivative respect to the y would be x z. And derivative respect to the y of this function, you better write it down in its partial form. So round g round y, if you like. Okay. Now you bring it from f of y. You see, from number 2, you substitute for f of y. So f of y is xz. xz minus e to the x sine of y. So if you compare them together, you see, if you compare them together, these are going to be canceling out. So the leftover is going to be just 0. Round g round y would be 0. So this means there is no y in g. So this means, you see, g is going to be kind of constant function. Okay, so the g of y is going to be a constant, but that constant can be a function of z. So you write it down as h of z. Then you're going to check it. Okay, any question? Instead of you write it down, because you have the partial respect to the y only, so this means this function is a constant. But your constant may be a constant, a function of z, because z is constant. Okay, now the next step is going to be, what is h of z? To get h of z, so you go back to your function. Okay, let's take the h over here, then differentiate respect to the z and use the equation number 3 to see if there is any z on it. Okay, so so far this means f of x y z is e to the x cosine of y plus x y z and plus maybe h of z. Okay, so this is the situation we're going to have so far, but we have to check to see what is h of z. So differentiate this equation with respect to the z. The function with respect to the z, this won't give you anything, but this would give you x times y plus h prime, and you compare it with f of z to see if there is any h in it. Okay. Any question? I want to go to the next page, continue. So I'm going to take the derivative of this one with respect to the z. That would give me 0 here, and that's xy and h prime. And then I can compare it with the equation number 3 to be able to find what is that function eventually. Okay, so I'm going to differentiate it. So f sub z, okay, partial respect to the z, as we talk about, is going to be 0 for the first one, and the xy and the h prime of z. Okay, so that will give us xy plus h prime of z. But from the equation number 3, okay, from the equation number 3, we already got the f sub z and the f sub z. From that equation, it's xy plus z. If you compare them together, then these two would cancel out because you let them to be equal to each other. Then the conclusion is that the h prime of z is equal to the z. Now we integrate it. That gives us the fact that h of z is going to be equal to the 1/2 of z squared. You don't need the constant c anymore. So this means eventually your function is f of x, y, z. It was e to the x cosine of the y, cosine y, okay, plus x, y, z, and you have the h of z, which is 1/2 of z squared. This is going to be the potential function of that vector field. Okay, any question? So this is the way we are going to operate. You will see it. When we get to the integrations, we need this function because you are going to be integrating through through a curve, those smooth curves that we talk about it. So as soon as we get this function, you'll be able to find it. So your result of integral is going to be evaluation of the function at the two endpoints of that curve that you have. So that's why we're just emphasizing to find these properties. If it's not going to be conservative, it takes time because we have to use the classic method to integrate. But most of the time, you are going to have these conservative. Okay, any question? Now we have two more terms that we have to introduce. These are going to be the ones that are going to be used at the end of the course, okay? When we want to compare the theorems together, but the crunch one is the one that we did, okay? But just this term, when you see in future, we have another quantity for future, and this is going to be called divergence or divergence, divergence, I think that's a better one, of a function. Again, they are going to use in electrical fields or magnetic field in physics, this type of ideas. So divergence of a vector field. We are not going to use it right through the end of our argument. We use it only once. But we may ask you on the next quiz to evaluate it. So you better have the formula handy. Okay, what is this one and why we like it? Remember so far, whatever we did, the result was a vector, vector, vector. So there is going to be a quantity that's going to be a scalar. And that would mean something and it's going to be used. So that's the divergence of a vector field. Now how are we going to define it? Remember the curl? There you are. Recall that as we did it, the curl of a vector field, of course, of a vector field F. Remember the curl is just defined by cross product. That's the curl. Curl of F is del cross F, which is a vector. It's a vector field, of course. Is a vector field. A vector field. Okay, divergence is going to be a scalar. In order to get a scalar, the definition of divergence is simply del dot F, not cross. If you do the cross, you get a vector. If you do the dot, you get a number, a scalar. That scalar is called divergence of the vector field, okay? So the divergence or divergence of F is a scalar field, number. It's a function, but it's a real value function. Is a scalar field that is defined by, this is it, divergence, div of F is del dot F. So it's very easy to find. How are we going to find it? This is it. You see the del is just a partial derivative operator. Round x, round y, round z. Dot function vector field m n p. Remember dot product? You multiply these components together. It's like a composition this time. So the divergence of F is going to be equal to round m, round x plus round n, round y plus round p, round z. That's it. This is the divergence, which is very easy to find. And it's a scalar valued function, okay? Because there is no ijk here. We are not going to use it, but if the divergence happen to be equal to the 0, they have a name for this one. Then it's the way we're going to apply it in physics. Then F is said to be a divergent force. Divergence force. The other one is a potential one, but this is going to be the one. Okay, so this is the only thing that we have to know. There is a point problem in your book. Sometimes, this is a kind of observation. We don't need it. The observation is the divergence of the curl of the F. Look at this one. Is going to be equal to the divergence of the curl is a del cross F. And remember, this is a dot product. Divergence is del dot. So it's going to be del dot, del cross F. Remember triple product? When we get triple product, if two rows are going to be the same, this is always 0. So this is one observation that some people, they like it. I just write it down as a record that this is going to be the case. Okay, we are not going to do much about this one, except one form of the integral that we talk about at the end. So the only problems that you have, okay, for this in your assignment, or we may give you one of them to find on the quiz, just to find it. A vector field would be given to you, ask for the divergence of the F. This is your formula. Make sure you know it. It's not going to be any other application of this. Okay, so let's give you that example to finish it. But conservative force is the one that we are going to use. So the only example that we can have on the divergence on this one is we have one question on the comic quiz. They give a function and we ask you to find all these quantities for us. So find the divergence of this. That's it. Divergence of the function f of x, y, z equal to x, y, z, I plus x, y, j and the zk. They ask you to find it at the number 2, 1, 1. You find it first, then you plug in this number to get a number. Okay, you know the formula. You see, this is M, N, and P. And the formula for the divergence of F, type of F, is round M, round X, plus round N, round Y, plus round P, round Z. That's it. Just substitute. Equal to derivative of M respect to the X. This is it. If of X is 1, Y, Z, plus if of N respect to the Y, X, of P respect to the Z, 1. That's it. So this is the divergence function. As you can see, it's a function of a real valued function. Okay, they want that at 2, 1, 1. It's like a function, divergence of the F at 2, 1, 1. Substitute. So Y is 1, Z is 1, X is 2, 1. So that gives you 4. 1 plus 2 plus 1, 4. So the divergence of F at those points, or at that point, is going to be 4. And you're done. Okay, that's all the preliminaries that we need to be able to talk about the integral of these type of functions. Okay, any question? So the message is the one that we did. A function with a vector field would be given to you, you test it. You test it to see if it's conservative or not. That function can be a function, a vector field in R2 or in R3. We don't need anything else really. Just these two, make sure you remember it. And then we are ready to take the integral of this type of function. It's going to be quite interesting. So that's it. Any question? So no question from this one on the test 3. So we practice tomorrow. I'll go over that practice test that I've already posted for you because we need the solution of those so that you can keep them for your final. So I do that one and then take your test early next week. And then starting Monday, I talk about those integral, line integral. If you have two types of integral, we give you one of them in 15.2 and the other one is in 15.3, 53 and 54. These are the one that we are going to cover. So before your next quiz, everything is already done. So we can check it on the quiz and then we can check it quickly on the final. That's it. Any question? So have a good one. Practice test number 3 tomorrow. Okay, let me know if you need anything. Bye-bye.